Hi, class. So today we're finally going to do it. We're going to step off of planet Earth and we're going to start thinking about looking for life elsewhere. So we're going to begin by surveying the solar system. So today we'll talk about the planets, and on next lecture, then we will talk about looking at the moons around many of the planets, because some of them also are good prospects for places to search for life. So in the image behind me, this is a picture of something called the family portrait. It was taken by Voyager when it had sailed past the orbit of Neptune. So this is in 1992, I think. And they gave Voyager one last command to use its cameras. It turned back and looked to the inner solar system, and it took a series of 72, I think, photos trying to capture all the worlds in the solar system together in one family mosaic. Now, the reason I'm showing you this picture is because it really illustrates the difficulty that we have even of looking for life here in our own solar system. All of these worlds are just specks of light, and we can look at them with our telescopes, but getting up close is really, really hard. And we'll talk a little bit about exploration, sending spacecraft to these worlds, but even so, we've only made just minor attempts to explore these worlds that are even very, very close to home. We have not explored them very much at all. And so our understanding, our knowledge, our confidence in whether or not we've searched everywhere we could search for life here in the solar system is actually very limited. And so that limit to our confidence is going to extend even more when we look out to other worlds in the galaxy. Okay, but that's for a couple of weeks from now. So today we're going to start by looking around the solar system. So here in the first half, let's just talk about a few considerations, and then the second half of lecture today, we'll do a tour of all the major planets and talk about what the prospects for life there are. Okay, so I'm going to go ahead and start a few slides. Okay, so you know, you see these kinds of family portraits all the time. I like this one a lot because it shows kind of what the core things we're thinking about in the solar system are. The sun is certainly the primary source of energy, although as we've seen, life can exploit various kinds of energy, and we'll talk about this when we talk about various places in the solar system. The primary planet we know about is Earth there, of course. You see Mars there in the lower right foreground. And in addition, if you look closely there in the halo of the sun, you see a smattering of small worlds. And it's really the small worlds, I think, in the solar system beyond the planet Mars that are the most likely places we might find life. And we'll talk about that more next lecture. Okay, so what I want to start with is we'll talk about what we think matters. We'll go through that list of considerations we've been talking about what life requires, and then use that to make a set of logical criteria that we're going to use to think about each planet critically when we encounter it. We'll talk about how we've learned all of these things and how, and then we'll talk about the big picture of the solar system to set ourselves up for the grand tour during the second half of lecture today. Okay? So by this time, all of you know that I'm a big fan of books, and so I'm certainly happy to recommend books to you that you can go read on your own, that you can have on your coffee table if you want to expand or develop your understanding of this more, or just indulge your curiosity. These are certainly good books. The one there in the back on the left called Our Universe by Roy Gallant is a book that really has been a rich part of my interest in astronomy. It was put out by the National Geographic Society. It has just exquisite artwork in it, and just does a whole survey of the solar system. So I'm showing it you here today because we're talking about touring all of the planets, and this book has basically a chapter on each planet. And so it's a very nice book if you can still get your hands on it. I don't think it's still in print, but it's very easy to find used copies of it. This book here on the lower left, The Grand Tour, this is by a very famous science author named William Hartman. He wrote it with Ron Miller, and it is, as we're discussing today, a tour of each of the planets in the solar system, what kinds of things you might encounter if you go there. It also surveys and talks about the moons. This book over here on the right is one that you can still get. If you walk into a Barnes & Noble, you can usually still find it on the shelf. I've actually used this book as a textbook when I teach intro astronomy in the past. It's one of the few books that students often keep because it's meant to be a coffee table book. It has exquisite photography, and the reason I like it is it basically has 2 or 3 pages about every topic in astronomy that you might be interested in. So if you're interested in asteroids, there's 2 or 3 pages on asteroids. If you're interested in quasars, there's 2 or 3 pages about quasars, and indeed there are a few pages about each of the planets in here. Okay, so there's a few books that you can add to your library. Go check out from the library when they're open if you're interested in expanding your background a little bit. Okay, leave them on the coffee table. Impress your friends when they come over for Dungeons and Dragons games or barbecues or whatever. Okay. So let's remind ourselves what we thought about life. So our biases in our searches for life, as we've been discussing for the last couple of weeks, are largely related to how we have encountered and learned about life here on Earth. And so the easiest thing for us to do is to imagine that life we find on other worlds is going to be more or less like life on Earth in terms of what it does for its chemistry and what it needs to survive and the kinds of environments it might inhabit. Now, those biases may deceive us. We may be completely wrong and find life in very unusual and very difficult to survive places for life here on Earth. We may find life that has completely different chemistry than our own. There's all kinds of ways that those biases could be wrong. But by and large, that this is what we understand is the easiest thing to look for, particularly here in our own solar system. You'll remember last time we talked about this notion of panspermia, where organisms could move between worlds from ejected meteorites that get thrown off a planet when it gets hit. And so that certainly suggests that if life were to spread through the solar system from one central point, Earth or some other planet, that it would all need similar kinds of environments to survive. So I've divided these into 2 separate groups, the so-called necessities, things that we think are essential, and then things that are considerations, things that we know would influence life here on Earth, and so we should just think about it when we're trying to decide where in all the vast places in the solar system we're going to look for life that we want to expend our effort, okay? So the first necessity is water. So we are very definitely biased towards water. Everything that we know about life here on Earth is that water is essential to life processes. It's used in the chemistry of life. Life lives in it. It's an excellent solvent. It's liquid over wide range of temperatures. And so it's useful in many different situations, okay? As a molecule, some of you may know that water is a kind of wedge-shaped molecule. It's got the oxygen down at the point of the wedge and then the 2 hydrogens out by the ends. It's that wedge shape that gives water some very nice properties. That exposed oxygen of that wedge shape allows it to bind to many different kinds of molecules, which is one of the reasons it's such a good solvent. So water has a lot of really great properties just in terms of chemistry, and life, at least here on Earth, has learned to exploit the water for its own chemical processes. And so this is why we think it's likely necessary, or at least a good ingredient in life that we might find elsewhere. The second necessity, as we've talked about, is raw materials. One of the processes that defines life is life takes in materials from its environment and then it uses those materials to do its lifey business. It creates copies of itself. It makes food that it stores, and all the things that it does with raw materials. Now, when we say raw materials, we're usually thinking about carbon-rich materials because, again, we are carbon biased because we are carbon-based life forms. Carbons form the central chains of organic molecules, and they are extremely flexible and extremely usable in many different shapes and configurations, as we've discussed. And so again, it kind of makes sense to our carbon-based brains that carbon seems like the most likely thing that life might exploit elsewhere. So when we're looking for places for life to survive, we're looking for places where there might be raw materials. And when we say raw materials, we mean organic molecules or carbon-rich environments. So lastly, life needs a source of energy. So life certainly uses energy. It takes in energy from its environment. In the Earth's ecosystem, that almost always starts with the sun. and then like plants photosynthesize it, and then we eat the plants and we get our energy from the plants, but originally that energy came from the sun. Okay, so sunlight's often the core source. That's what we mean by that. But as we've seen, life is very clever here on Earth, and there are many places where it has managed to figure out other ways to gain energy from the environment. So the kind of obvious example is the black smokers, the hydrothermal vents that we see on the ocean floor, where the life forms there in that ecosystem have learned to utilize the heat and learn to use the high sulfur environment as a source of energy. Remember, we call that chemosynthesis, using chemistry for energy. Okay, so those are the three basic criteria. So anytime we look at a planet or a moon or just some location we find in the solar system, and we want to say, is it likely we might find life here, we're going to look for these three items. Is there likely water? Is there likely raw materials? Is there a good source of energy? And if we find all three of those things, then we'll be like, okay, maybe this is a good place to look for life. Now, there are other considerations, things that aren't essential for life, not the way these top three items are, but things that certainly could inhibit or enhance the ability of life to survive. Okay, so one example of a consideration is the atmosphere. So life on Earth very much benefits from the fact that an atmosphere is here. The atmosphere regulates the environment. It helps control the temperature and the energy flow to and from the Earth. And it also transports materials around the planet. It moves water. It's a central player in the water cycle on Earth, but it also moves materials. Dust and things blowing in the wind move from one place to another. Life has certainly learned to exploit the atmosphere. So if you look at things like plants, dandelions certainly spread themselves around because the atmosphere blows them around so that their progeny can find new places to colonize and the species can survive. So the atmosphere is certainly a big consideration. As you and I both know, we've certainly found life in exotic places. So there is no atmosphere on the bottom of the ocean, but there is an ocean that acts in many ways similar to the way the atmosphere acts. So anyway, so it's a consideration, but it's definitely not a requirement. It can certainly help life. A second consideration, which we haven't talked much about, is protection from radiation. So particularly in outer space, the radiation environment is very strong. There is strong radiation from the sun in the form of what we call the solar wind, particles coming off the wind, off the sun at very high speed. There are also what we call cosmic rays coming from outside the solar system. And so these radiation particles, with life on Earth in particular, they can be very damaging to life. So this is why we don't like you to be exposed to lots of X-rays. We don't like you to be exposed to gamma rays. We don't like you to be exposed to excess ultraviolet radiation, right? All of those things are damaging to the structure of life on Earth. It damages cells, and in particular, it damages genetic material, RNA and DNA strands. And so some of that's good because damaging DNA strands, for instance, can cause mutations, and mutations are where we get new species from or where species evolve from. But those kinds of spontaneous mutations could be advantageous or they could be disadvantage. And so it's not clear that random mutations always helps you survive when you've evolved to be very adapted to a local environmental niche. Okay, so on the Earth, we are protected from radiation by something called the Van Allen radiation belts, and that's associated with the Earth's magnetic field. Many planets have magnetic fields and certainly have radiation protection of that sort, but not everywhere. Okay, so that's something we might consider. Another consideration is temperature. Now, temperature plays a very strong role in energetics, both in terms of the environment that the life finds itself in, because it can certainly extract energy from temperature gradients. So we saw that in the hot springs in Yellowstone. But excess temperatures or very low temperatures can certainly destroy and damage life that we see here on Earth. And so it also plays a role in environment changes. So temperature is largely responsible for the driving of the climate system. And so the atmosphere transporting things around the planet, that's largely driven by temperature gradients on Earth. Okay, so temperature is an interesting thing that we will consider. We will certainly find places in the solar system where we think it's too hot for life, and places where we think it's too cool for life. But by and large, it's something that certainly can play a role in how life adapts to the environment that it finds itself in. Okay. And then the last example of a consideration is something we talked about last lecture, that is the gravity of the planet, the surface gravity. That certainly influences the life form itself. So you and I can exist as upright walking around creatures because our bodies and the mechanical structure, strength of the materials that our bodies are made of can withstand the gravity on Earth. But you can imagine if the gravity was 100 times stronger, that it would be very difficult to walk. Okay, so gravity can certainly play an intense role in the environment that the life finds itself in, but it also influences the formation of the planet. So we're going to see many different planets here in the solar system. They form the way they are because of the strength of their gravity. When we start talking about exoplanets, we'll come back to that point. So there's a variety of ways that gravity could be important on a planet. The most important way that it's going to be important on a planet that we're going to see today is that gravity is largely responsible for whether or not a planet can hang on to its atmosphere or not. Okay, so we'll come back to that point as we do our survey of planets in the next half of the lecture. Okay, so let me tell you a couple of things about energy. So the intensity of light from the sun is really the regulator for how much energy you have available to you if the sun is the source of energy. Okay, and so some of you may remember there's something called the inverse square law. So imagine you have the sun sending out a bundle of beams of light. Okay, so these beams of light are represented by these nine arrows coming straight out from the sun. So if I'm at some distance away from the sun and I measure the area covered by those 9 arrows, so that's that box labeled A there, that is basically a measure of how bright the sun looks like, basically how much light falls on a given area. Okay. Now, if I let that light travel on its merry way farther out into the solar system, what the inverse square law says is that if I double my distance from the sun, what I find is those 9 beams of light that used to just go through that one square A, if I'm twice as far from the sun, those 9 beams of light now cover 4 squares of A. Okay, so this is why it's called the inverse square law. I'm twice as far away, so 1 over 2 squared is 4. So the light spread over 4 times as much area, or equivalently, the sun is 1/4 as dim. Okay, and similarly, if I go 3 times farther away from my original position, the light is now spread over 1 over 3 squared, or 1 over 9. So it's spread over 9 times the area, or the sun is 1/9 as bright as it was. Okay, so the consequence here is we enjoy a certain amount of energy here on Earth because we're at a certain distance from the sun. And if we get closer to the sun, that energy will be more intense. And if we get farther from the sun, that energy will be less intense. Okay, and that has consequences for life drawing energy from the sun. Now, temperature is also intimately related to the parent star, the sun in our case, and that's because the sun is the primary input of energy to the planet itself. There are other ways for the planet to generate energy, in particular deep down in the core. Radioactive processes can generate energy, but by and large, most of the energy on the surface where the life is living comes from the sun. So the sun sends out light, and the entire surface or the side of the planet facing the sun is bathed in light. So depending on the surface, it will absorb some of that energy and heat up. It may reflect some of that energy, okay? But all of the energy that's affecting the planet's temperature is coming from that input energy from the sun. Now, that doesn't completely determine the temperature, because just like if you heat something up, like if you stick your coffee or your tea in the microwave and then you set it on the counter, if you hold your hand around the outsides of your cup, you will feel heat radiating off of your cup. And a planet is the same way. If a planet heats up, then it also spits energy out back into outer space. And so the temperature that a planet has, the temperature that life finds itself immersed in, is about the balance between the incoming energy and the outgoing energy from the planet. Okay, and so the properties of a planet greatly affect that. Atmospheres have insulating effects, so they will reduce the amount of energy that is re-radiated out. Clouds, rock, and ice affect how much of that incoming radiation is absorbed or reflected and never changes the temperature at all. Okay, so all of these kinds of things affect how a planet responds to that external environment, and then that is what fixes the temperature that the possible life form on that planet might find itself in. Okay, so curiously, and much to our great benefit, you and I are alive during the few moments where we have completed, for the first time in history, the complete reconnaissance of the solar system. It began during the space age. When the space age started, we first had rockets, and we were able to start sending space probes into space. The very first planet we explored was Earth, right? So the very first rockets launched satellites, which were basically satellites that looked back at Earth or looked at the Earth environment. So the Earth was the first planet explored by spacecraft. But over the ensuing 50 plus years, we have sent spacecraft to all of the major worlds in the solar system. And that reconnaissance has just been completed in the last 5 or 6 years with the visitation of Pluto by New Horizons and with the visitation of Ceres in the asteroid belt by Dawn. Okay, so every major world has now been explored, some of them many more times than others. So now we have our first complete up-close viewing of all the major worlds in the solar system. And that will inform a lot about our understanding and where we're going to look for life in the solar system. Okay? So the architecture of the solar system, we've talked about a little bit before. You remember we made our maps of the solar system at the beginning. I've distorted that map here and put everything on one slide again. But the architecture of the solar system is very provincial. There are basically 3 neighborhoods that we think about worlds in the solar system. And in those 3 neighborhoods, all the worlds kind of have similar character. Now, just to illustrate our bias about the universe, we often used to think that this was the way solar systems formed themselves. And once again, you and I live in the future, and it's only in the last 10 years or so where we've discovered enough other solar systems around other stars that we've discovered that architectures can in fact be quite varied. Okay, and that greatly influences what we think about this whole problem. But here at home, it divides itself up into three neighborhoods. So that inner neighborhood are what are called terrestrial worlds. Terrestrial means Earth-like, okay, like Terra. So what we mean by that is small worlds that have rocky surfaces, okay? The next zone are called Jovian worlds. So Jovian means Jupiter-like. Sometimes these are called gas giants. You can see 2 of them are much bigger giants and the other 2 are smaller giants. So sometimes we call these the gas giants and the ice giants, but these are all the so-called gaseous or Jovian worlds. And then there is this third zone where Pluto has lived, and much of the arguments about Pluto have been associated with the sorts of stuff that we find out there in the third zone, and we'll talk about that eventually. Here it again is laid out to scale. Okay, and the reason I laid it out to scale is because that third zone is actually enormous. It goes out way farther than just the end of our solar system map that you and I made during the first week when we printed out our folded pieces of paper. That third zone includes what's called the Kuiper Belt. So this is a vast region out past Pluto. And beyond that, there's another structure called the Oort cloud, which surrounds the entire solar system. But the Kuiper belt is largely filled with small icy bodies. Very few of them are the size of Pluto at all. But these are the detritus, the flotsam and jetsam left over from the formation of the solar system. So they're very primordial. They have lots of the early volatiles. And when we talked about the delivery of volatiles to the Earth via comets, this is the kind of region and these are the kinds of bodies that brought the original volatiles in. Okay? Now, since we're talking about Pluto, let me talk about Pluto just for a minute. So we're going to include Pluto in our discussion of planets, okay? Now, I am not going to comment on the fact that most of the astronomical community is wrong when they call Pluto a planet. I am not going to comment on the fact that Pluto has been unfairly demoted from planethood, and it really should be included with all of the planets. Okay, I have no strong opinions about whether or not Pluto is a planet or not. Okay, and if you believe that, I'm sure I have some real estate somewhere I can sell you. Okay, if you're interested in a little bit of extraneous watching, you can go watch a TEDx talk I did at Northwestern in 2014 about Pluto and about what it means to be a planet. We will talk a little bit more about that when we start talking about exoplanets, because it's in fact the discovery of exoplanets that really should be driving our consideration of what a planet is or not. But for our discussion here, we're going to include Pluto within the planets. That's to separate it from our discussion of moons, which we'll do next lecture. Okay, so that is all I'm going to say right now. So I hope you all are reading. This is all the chapter about life in the solar system in the book. So take a gander at that. The next half of the lecture, we'll do a tour of the solar system and talk about prospects on each of the planets in the solar system. And then that'll set us up for our next lecture, where we talk about life on, or possible searches for life on the moons of the worlds in the solar system. Okay, so have a good night, everyone. We'll talk to you soon.